Welcome to another lecture. This week we will explore the second part of data pre-processing that we started last lecture. So this time we will discover some data transformation tasks. We'll talk about feature engineering and we'll explore some strategies for handling imbalanced data sets. So these procedures, among others, are really crucial for preparing your data for effective modeling. So when we talk about the data integration stage, so last time we already covered data cleaning. Now for data integration, we often pull data from multiple sources, as we said. So think of customer databases, transactions, logs, even external APIs. And in this stage, we try to combine the data into one single unified format so that everything can be analyzed together, right? Now let's move to the next stage, which is data reduction. So big data sets can be overwhelming and inefficient. So here we'll discuss the reduction of the data set size without losing meaningful information. So there's many ways one could apply data set or data reduction. We could go for a dimensionality reduction, which actually reduces the number of features or attributes, or we could go for a numerosity reduction, which actually reduces the number of instances this time, not features. Or there's also data compression, like for example when you are compressing PNG image into a JPEG with a lower resolution, for example. Okay. Sometimes instead of working with the entire data set, we can work with a smaller representative sample, and this is called sampling. And it's a form of a data reduction that helps make analysis more efficient, especially with large data sets. So the key is to ensure that the sample accurately reflects the distribution of the full data set. So for example, if your data is skewed or has an imbalanced groups, simple random sampling might not perform well. So you will need something more advanced like stratified sampling. So when working with large data sets with a lot of instances, as we said, we sometimes want to reduce the size, but without losing the essential patterns in the data, right? That's where we use sampling, which is a type of a numerosity reduction, or we are trying to reduce the number of instances, not the features. So there's many ways to do sampling. First of all, random sampling, right? So here we try to give each item an equal chance of being selected. So it's a simple and biased way, but not always efficient, right? Then there is sampling without replacement, and that's where once a data point is selected, it is removed from the pool, right? And this ensures diversity in your sample. In contrast, we have sampling with replacement, which allows repeated selections of the same point, and it's useful for some cases like when we're doing bootstrapping, for example, which we may talk about later in the course. And then finally, we have stratified sampling, which is a smarter approach. We divide the data into meaningful subgroups like customer types or regions, and then sample proportionally from each one of these groups. And this helps preserve structure in imbalanced data sets. So the other type of dimensionality reduction is reducing the number of features, or what we call feature selection, right? And here the question is which features to keep in your model and which ones to leave out, right? And that's where different methods for feature selections come in handy. So this chart right here shows three main approaches to do feature selection. You can either go for a filter based, and these are simple and fast, and they are model independent. So your model that you're using in the modeling stage will not take any part of this task right here, right? So here you evaluate each feature on its own, right? Separately based on some statistical tests. So examples, there's Pearson correlation, F statistics, the chi-square statistics, and so on. So you use these to filter out features that show very weak relationship with the target variable or with the class or label, right? On the other hand, we have wrapper methods. These are more computationally expensive, but often more accurate, right? So here you train a model repeatedly on different subsets of features and then keep the combination that performs the best, right? So there's the recursive feature elimination, and there is also the sequential feature selection. Provided in the supplementary material, some some optional read-in assignments for you to explore how each one of these work and how to implement them in Python. And then lastly, we have embedded methods, and these combine feature selection directly into the model training process, right? So some algorithms, they naturally identify the most useful features while training. As an example, we have random forest. There is also the lasso regression, right? So for these, you do not need to do any feature selection. The model itself handles this part. So let's move to, so we've talked about so far cleaning, integration, reduction. Let's move to the last part here in the pipeline, which is data transformation. So to transform the data from the original space into a newer space, and that's usually because the data in the new space would perform better and would make your model work best. And so there's many ways to transform the data. We have smoothing right here, which helps remove noise or fluctuations in the data, especially important in time series, right, or sensor data. So you might use moving averages or binding to smooth things out, right? And then next we have feature engineering or data enrichment, and here we create new features from existing ones. For example, if you have purchase data, you can extract data of the week or holiday versus regular day. These new features often make your model smarter, right? And then we have aggregation, which involves summarizing your data, right? Think of the total, the average, or group by, right? It's also how we build data cubes in OLAP systems. So if we get to talk about data warehousing and OLAP systems, that's the aggregation data transformation type here is very useful. Next, we have normalization. That's very common. It's all about rescaling the values of your features, right? So they can fall within a standard range, right? X and Y. So to do normalization, the common one is min-max normalization. This one maps the values between the 0 and 1. 0 and 1. There's also the z-score normalization. This one centers the data around the mean of the feature. There's the decimal scaling, which moves the decimal points based on a value, on value size. And then finally, there's discretization. And this one converts continuous values into categories. For example, instead of modeling with raw age values, you can group them into age bands like 0 to 10, right? And then 11 to 12 and so on, right? And or you can just label them youth, adult, senior, and so on. This is an example of raw data, right? This one is raw data. We have two features here, the length and the whole weight. And this is the what the data looks like after normalization. This is the min-max normalization, as you can see here in the formula, right? So the values of the features, as we said, fall between 0 and 1. On the other hand, this is another type of normalization or standardization, right? So here we subtract the mean. This is the mean. Sorry, this is the U, or let's just call it the mean. And then this is the standard deviation. So we subtract the mean and we divide by the standard deviation, and this is what the result looks like for the standardized data. So another type of data transformation is nonlinear transformations. These are a powerful way to make your data more normal looking, which is often a requirement for many statistical models and also machine learning models. So in this example right here, you see a histogram of the whole weight feature, right? The original data here on the left is right skewed, right? Meaning most of the values are small with a few very large ones. So by applying a square root transformation, the distribution becomes more symmetric, right, and bell-shaped. And this transformation reduces skewness and helps make the data more suitable for models that assume normality, right? There's other common nonlinear transformation, which includes the log, square root, and so on. Another type of data transformation is discretization, and as we said, it is the process of converting continuous data into discrete categories or bins, right? So here you can see equal width binding, right? This method divides the range of the data into intervals of equal size. They have exactly the same size. It's simple, but can lead to some uneven distributions, right? Especially when the data is skewed. Right here, we have equal frequency binding, right? So here each bin contains approximately, right, the same number of instances, right? So this helps balance out uneven distributions. And both methods have trade-offs, right? So equal width here is easier to interpret, while equal frequency can reduce the dominance of outliers, right? And then choosing the right method depends on your data's distribution and your application as well. So most common challenges in data preprocessing is encoding categorical variables. So here you will notice that we have the sex column right here. It has 3 categories: the female, male, and infant. So machine learning models can't really process these text labels directly. So we have to convert them into numbers. And there is 3 popular encoding techniques. The first is label encoding, right? So this method assigns a numeric code to each category. So female becomes 0, right? Male becomes 2, infant becomes 1, right? It's simple and efficient, but sometimes it creates some unattended ordinal relationships which sometimes could confuse the model, right? There is no really order between male, female, and infant, right? But the 0, 1, 2 may give that impression. The next type of encoding is one-hot encoding. This creates a separate column for each category, and then if a row belongs to that category, it gets a 1. Otherwise, it's a 0. So it avoids any implied order, and it is safe for most models, right? The last type is binary encoding. This is a hybrid method that first label encodes the categories, right? So you first go by label encoding, and then it converts the number to a binary form. So it is a more compact option, right? Especially useful if you have a lot of categories and you want to reduce the number of columns. And then we have feature engineering, which is the process of creating new features from existing data to help your model learn better patterns. You're essentially building better signals out of raw features, right? For example, if you have a date column, you can extract the day, the month, or flag whether it's a holiday or no. So these new features might help explain purchasing behavior in a retail data set, for example, right? You can also engineer features from text, like counting the number of words in a review or calculating a sentiment score. And in numerical data, you might create ratios or differences between columns or even multiply variables together to reveal interactions and new patterns. Now let's talk about this problem of imbalance in your data. So this happens when one class in your target variable massively outweighs the other one, right? For example, imagine you're building a fraud detection model where 99% of the transactions are legit and only 1% is fraud, right? If you train a model on that data, it might learn to just predict legit every time and still achieves 99% accuracy, right? That sounds great, but it completely misses the point because it's failing to catch the fraud. This issue is common in many real-world scenarios, things like spam detection, as we said, disease detection, and so on. So because many models are accuracy driven, they treat all mistakes equally, right? But in imbalanced data sets, some mistakes may matter more than others, right? So misclassifying an affected patient may be much more costly than misclassifying a healthy one, right? So you should never trust high accuracy blindly. You should always check the balance of your data before training. So how do we deal with or how do we reduce the impact of class imbalance? We could go, some of the two simple methods here is upsampling and downsampling the data. So for upsampling, this means to simply increase the number of examples in the minority class. We do this by duplicating existing examples or generating synthetic ones using techniques like SMOT. So this gives the model more opportunity to learn what those rare cases look like, whether that's fraud, defects, or whatever. So it's especially helpful when you have too few positive cases to train effectively, right? On the other side, we have downsampling, right? And this reduces the number of examples in the majority class, right? So we do this by randomly removing raws, making the data set more balanced. So it's useful when your data set is very large, but it does mean throwing away some data, right? So you need to be careful not to lose important patterns. So in sum, data transformation and feature engineering are essential steps in preparing your data for modeling, and addressing imbalanced data sets is crucial to ensure your models are trained fairly and perform well across all classes.